Good morning, everyone. I'm Dr. Tanadet Polkai, and I'll be discussing some of the concepts that I've been very interested in both doing my research and also a bit of a teaching on membrane bioenergetics, which basically we'll be talking about how molecules diffuses across the phospholipid bilayer, and we'll be investigating the mechanisms on it and the thermodynamic principle of it. So the first thing I want you to have a look at is this system, where on the left side I have several potassium ion, about 13 of them on this side, and also these molecules, which are glycerol. Now, assuming that the membrane here are freely permeable to both potassium ion and glycerol molecule, which is polar and small, can diffuse across the bilayer. What do you think will happen to the system in equilibrium? If I left the system to be equilibrated in equilibrium, what do you think will happen? I'll give you 20 seconds to think about this, and then we'll move on and work from there. Right, 20 seconds has passed, and now we'll be thinking about this together. So I assume that most of you would have thought that the glycerol molecule would distribute evenly on both sides. So if I have 10 molecules here, I have 10 molecules here, I'll end up with 5 and 5, 5 on the left side and 5 on the right side. And that's very common to think about that. It's very intuitive because if I spray a perfume on one side of a room in a volume specific closed space, if you leave it there, you probably on the other side of the room and you probably smell it because the gas diffuse evenly, with an even concentration across the room, and that's diffusion. However, for the potassium ion, it's probably not going to follow that pattern. And the reason is because when you leave it to diffuse, you're going to have a buildup of positive charge on the other side, and that's going to push back the new potassium ion that would like to diffuse, that is thermodynamically favorable to diffuse. And therefore, you won't end up with an equal concentration. The question is why and how can we define this thing? So we'll be looking into that concept today. So the objectives of today's lecture is that we'll be looking to relate thermodynamic principle to the formation of a concentration gradient. So how can we think about the thermodynamic process behind this? We will then derive the Nernst equation, which explains the relationship between the ion concentration on both sides and the equilibrium potential. So what will be the potential difference across the bilayer when you have just one single ion species, and explain why that specific potential is very important in the context of potassium ion. By explaining that, well, biology is not just about potassium, it's about sodium and chloride as well. So we'll be thinking about how we can apply the Goldman-Hodgkin-Katz equation to predict the overall resting membrane potential by looking at multiple competing ions and their different impermeability across the membrane. We will be looking how to model the new neural membrane. So how can we think about the axon and how can we generate action potential using circuits diagram? And lastly, we'll be thinking about how we can interpret the Hodgkin-Huxley model and explain how voltage-dependent conductance can drive molecular membrane dynamics over time. So how can different conductance of each ion can lead to action potential firing over the period of time. Now, let's think of this case study where we have 10 glycerol molecule on the left-hand side, labeled as A, and the empty space with label as B. If I leave it to equilibrium, as we have discussed, we have 5 on one side and 5 on the other side. Now, I would like to bring you to some physics principles. I want to take you to some physics lecture and think about some physical principle here. So, on chemistry, of course. So when we think about this, the best way is that we treat a molecule as X, so we can formulate them, and we treat this as a dynamic equilibrium. So we have X in compartment A in equilibrium with X in compartment B. And this being in dynamic equilibrium, meaning in ensemble process, we will have equal concentration of A to equal concentration of B at equilibrium. And the rate of this molecule being in A side, moving to B side is equals to the rate of this molecule in B side moving to the A side. Now, I want to introduce you to a concept of chemical potential, or mu, and we can say that in equilibrium, the summation of a chemical potential of molecule X of multiplied by n, which is a number of moles, can be sum up, and together on one side will be equals on the sum on the other side. And this is based on the first and the second law of thermodynamics. And the first law of thermodynamics is that the energy in the system has to be conserved, so the total energy is the same. And the second law of thermodynamics is that we try to maximize the entropy. In this case, when we try to reach the equilibrium, delta G equals 0. So we try to spread out the molecules as much as we can. So maximize the entropy means maximizing the distribution of energy. Now, what is this mu thing? So mu is the chemical potential, which is basically the free energy per unit mole, per unit molecule. And that can be calculated with the standard chemical potential plus RT ln of the concentration. So the higher the concentration, the higher the chemical potential. Now, this chemical potential will dictate whether you can diffuse from one side to the other or not. And that mu naught X is a constant specific to a molecule, to an ion, to a compound, So that basically, this is specific constant, I is a constant, T is a constant. Now, if I leave this system to be at equilibrium, what that means is that I can have mu naught plus RT ln X on one side and mu naught plus RT ln X in the other compartment on the other side, starting from the same equation. And you can see here that these two cancel each other out, leaving me with RT ln XB over XA, because I take this to the other side and the subtraction of a logarithm is a fraction. Now, I have 3 case study. My R is a constant, so 8.3. So I can't have that being 0. My temperature won't be 0 because I'm not at an absolute 0. That leaves me with just ln xb and xa. And to have ln value equal to 0, mean ln 1, xb has to be equals to xa. And that explains why if I leave the system in equilibrium, I will see that I will have an equal concentration of xa to the xb on both sides. However, it's not that easy when we think about potassium ion, right? If I have a number of potassium ion on one side, I leave it in equilibrium, I'll end up with more potassium on one side than the other. And the reason is that as much as the chemical potential is pushing it to move to the other side, when it starts to dominate, the electrical potential, which means that these positive charge will start to repel and push back the positive ion, and therefore making it more cannot diffuse across anymore because of the electrical repulsion. Of course, inside of a cell, we know that there are more positive ion, and that's because there are other negatively charged molecules inside of a cell as well. Those are DNA or some inner leaflet lipids, which are negatively charged. Now, thinking back to the same process, we have potassium inside, in dynamic equilibrium, with potassium outside. The chemical potential potassium, instead of being defined by just mu naught plus RT ln C as the previous one with glycerol, now we have a new constant, ZFV, and V is the electrical voltage of a solution, so it's the electrical term. So now we have this thing because potassium is charged. And as you can imagine, we have the inside versus the outside. So we set up the same equilibrium scheme again, where we have the inside and the outside with mu n, mu k multiplied by nk, and this assume that n equals to 1. I can say mu k plus RT ln k inside plus that FV in equals to the same standard RT ln concentration plus that FV again. Now, mu is the same as mu, so I can cancel that out. I can move out to subtract in again, so that I have in minus out. So this is a relative thing. We always calculate the energy with out subtract in and in minus out, and taking the logarithm again by combining this, factorizing, I have ln out over in equals that F in over out, and I can call this potential difference inside relative to outside delta V. And I have this equation. Now, I want to understand the relationship between this delta V, which is the reversal potential across the membrane. What that is telling me is that if I have this distribution of ion across the membrane, what will be my reversal potential? If I leave the system to be in equilibrium, I have these different in ion concentration. What will be my potential difference across the membrane? And we can calculate that. And by rearranging the RT back on the other side, we got this equation, which is RT over ZF, ln K out over K in. And this is the relationship, and we call this the Nernst equation, or the reversal potential, or the equilibrium potential for this delta V term. Why is this useful? Why do we bother learning all the derivation of the physics of this? Why should we care? Why should we think about this? Well, think about our cell. Our cell is a system where you have potassium ion on the outside being 10 millimolar, potassium ion in the inside being 120 millimolar. And I have this equation, and I try to sub it in to get the potential difference. I'll get that the potential difference in my cell is approximately minus 65 millivolts. And that's very neat because our cell resting potential is about minus 70 millivolts. Now I'm going to give you another 10, 20 seconds to think what this might actually mean in biological context. Okay, so what does it actually mean is that it's very close, and that suggests that the cell is mainly permeable to potassium. Potassium can move in and out of a cell freely, and we get minus 65 millivolts. Meanwhile, if I take sodium concentration, I get plus 65 because it's just other way around, hypothetically. And that's not quite our steady state. That's not quite our normal cell. I've just told you that our normal cell sits at minus 70. But if I read the sodium, it gets plus 65. And that means that our cell is not permeable to sodium. So there must be some gate, some door for sodium as well. And why are they opposite? Well, because the concentration is opposite just this term, and this is the constant. And therefore, if I allow sodium to move into the cell freely, right, instead of having a negative 65, I'll start building up positive concentration, not positive voltages across the membrane. So instead of going from minus 65, I'll start building upwards. And that's why we got something called depolarization, where we go from minus 60, minus 70, all the way upwards to plus 30. And that is exactly what we get. So here we get a channel which are mainly permeable to potassium channel, potassium ion. And when we open the channel, we get through this little threshold and we get upward in depolarization. So this is sodium moving in, but it peaked at only plus 30. Why is that? It should have gone all the way to plus 70, right? Because if I say I let it reverse, it should, or at least it should go to plus 0, right? Because potassium and sodium should exchange. The answer is that it's not, because remember, the cell is not in equilibrium. It is a steady state. So you have an influx at different rate, an efflux of potassium at different rate. And because these things are not freely permeable, they have these little doors called ion channels. And these ion channels control the efflux and the influx of ion at different rate. And therefore, unitary conductance and how these conductance is letting the pores through is dictates how far can we go in these action potentials. And not just conductance, but also permeability as well. Now, I said it flow at different rate. It has different permeability to sodium, different permeability to potassium. Now, as I've just told you, the world is not about sodium and potassium. There are also other ions as well, also chloride. So we will start to think about how they can be open and close. And we are looking at this equation here called the Goldman-Hodgkin-Katz equation. So why do you think chloride has a sign swap? Just mathematically think about it. I just took the Z off here, but while chloride has a sign swap, why is that? Exactly. That's because chloride has a negative charge, and a negative of a logarithm is a fraction, so you swap the sign downward and upward. So basically, the sum of the concentration of potassium outside, relative, and sodium outside, and chloride inside to the sum of the other side, with this P here being a permeability constant, so how permeable the membrane is. Now, when we think about a cell, right? So we just talk about the cell, we have ion coming in and out. These things have membrane, and therefore ions will not go through the membrane because these things are hydrophobic, they are uncharged, but they are actually a very thin insulator separating charge, and therefore they have this capacitance ability. So we have one first thing, that if we have a capacitance, we have this capacitive current, which is membrane capacitance multiplied by the change of the voltage over time here, which is we're gonna call it IM. We can treat the cell here as a capacitance here, and also what fueling the ion to move through is the gradient. So the ionic gradient across the membrane behave as a battery. So if it's behave as a battery, then we got ionic gradient to push ion through, right? And we have this channel here where ion can go through, act as a resistor. So this is basically, if you think about a resistor, it is basically something in your circuit which makes the electrons flow through slower, right? It can or anything really. So it can be even the length of the wire itself can also be a resistor. In here, it's the ion channel. So this little protein gate that allows ion to go through at different rate, and this thing we denoted as GK. And you would normally think that the ionic gradient and this conductivity is just a reciprocal of a resistance. So ohm to the power of -1. This ionic current is equal to GE. But when you think about the driving force for just potassium ion, IK, will be equal to GK, which is the conductance for the potassium ion through potassium channel of the overall driving force subtracted by the potassium driving force. And when you do an experiment on electrophysiology, what you vary is this E. So we vary the potential difference across the bilayer, and we record the current, and therefore we know we can work out the conductance of an ion channel as this EK is a constant, because we know reversal potential of potassium. Again, biology is not about one ion. Biology is a system with many ions. And we will start to look, and that's why we have this system here, which is developed by Hodgkin and Huxley, who got a Nobel Prize in 1952. And this is the total ionic current, so IM, the current, multiply equals to the capacitive current plus the current from the sodium, current from the potassium, and the leak current, so the IL. Now, I would go through each term and explain how the ion flow differently in the system, starting from the leak current, which is very straightforward. It's the conductance of the leak current multiplied by the potential difference for the leak current. So similar to what I've just shown you in the past. But now we want to think about potassium. Again, we have Vm minus Ek, similar to what we've just seen. Then we have this Gk, and we have this N, which is another term, suddenly pops up. This N is a variable, and this is a variable varied from 0 to 1, right? It's not a constant, it's a variable between 0 and 1, which explain the channel gating variable. So it's the different gating properties of a channel, which makes sense. But why 4? And this 4 came from the fitting of the data. So by varying the E and the I, by varying the E, you get different I, and then you have different N specific to each E. So you have a system with multiple simultaneous equation, and you try to fit different exponential, and the number that fits best is 4 from experimental data. And that's very intriguing because when you wait about 30, 40 years later, I think about 40 years later, Rod McKinnon solved a structure with Declan Doyle, and the paper was in Science of a potassium channel, the first one, KCSA, the bacterial version of it. And they saw that the protein is actually a tetramer. What that means is that we were able to depict that it requires 4 subunits of protein coordinating each other to open the channel about almost half a century before they solved this structure. Almost half a century. That's almost like half a lifetime of a human. Yet we managed to see that there are 4 things required to coordinate the permeation of iron. How's that intriguing, right? From mathematical and physics fitting, we use that information to understand biology about half a century later. The third term is the sodium. And again, we have this G that we're familiar about. Instead of N, we have M, and we have this new thing called H. Again, M is a variable which exists between 0 and 1, which is the gating term. Why 3 again? It's to do with the fitting of the model. Does it mean that a protein has 3 subunits? In fact, no. If you look at the sodium channel, they are not a tetramer. They are definitely not a tetramer. They're actually a monomer, but they have a 4-fold symmetry, which makes the story even worse because you managed to fit it to 3. But why 3? It is 3 because you required 3 subunit to be activated to be open. So you don't need all 4 domains, sorry, not subunit, domains to be activated, to be open. You only need 3 domains to be activated for the sodium channel, voltage-gated sodium channel, to be open. H is another probability term for this gate. Sodium channel is different from potassium channel. Potassium channel, open, close. Sodium channel has this other gate here, lower down, called inactivation gate. We call this the ball and chain mechanism, where we have open state and we have this ball coming downwards to plug the ion channel close. And this is a probability when the channel inactivation gate is not blocking the pore, so when it's allowing the ion to go through. So sodium channel, almost like a timer, it can open for a certain period of time, then it would decay itself to shut down. And hence why, when you go to the top, at certain point, you reach the peak because the system deactivated itself. The sodium channel deactivated itself. Before I finish this lecture, I want to end with the exit question by looking at this action potential and which term in the Hodgkin-Huxley equation do you think changes during the depolarization? Is it the capacitive current, the sodium current, the potassium current, or the lead current? It is the sodium current. And you peak there because of the inactivation of the sodium channel. That's all you need. Right, take-home messages for this lecture is that the concentration gradient will create a physical drive for the molecule to move. For any single ion, there is a specific voltage with the electrical push exactly cancels the chemical pull. Right, the chemical concentration is pushed back by the electrical buildup. The real cell is permeable to multiple ions. The final resting potential is a weighted compromise between all the ion, and we look at what ion is most permeable. Now, chloride concentration is about the same on both sides of a membrane. But what do you think might be happen in a context if a cell has a chloride channel suddenly become more open, so the cell become permeable to chloride? What do you think will happen to the cell resting potential? I'll leave that question to you. We'll discuss that in our next lecture. Thank you very much for your attention, and I look forward to take any question. Thank you.